Continuing with our applications of integration, let's now talk about total distance. And in particular, I want to distinguish between the notion of total distance and displacement. So to set up the context here, consider a car traveling along the x-axis. At any moment in time, the driver can determine how fast they are going, let's say in kilometers per hour, by looking at the odometer. This is called the speed. So let's think of this as a function speed of t, of the car at time t. However, only looking at the odometer, the driver can't tell the direction in which they are traveling. So in order to indicate traveling in the positive or negative direction, we need to multiply what we see on the odometer by plus or minus 1. So if we're talking about that, that's going to be the velocity of t. So thinking of that again as a function of time t. So importantly, notice that both speed and velocity have the same units here, kilometers per hour. And the connection is that the speed as a function of t is equal to the absolute value of the velocity as a function of time t. So that's the connection here in terms of wanting to be able to indicate a direction or not. So now, if we start to think about the difference between integrating speed with respect to t or integrating velocity, so let's think about an integral from a to b of my speed as a function of time t. So what we want to think about the result here, thinking of our units, if we're talking again about time measured in hours, speed is kilometers per hour, time is hours, so the integral would give us a scalar with units kilometers. Because the speed is measuring the rate at which the car is traveling without regard to direction, if you're going to aggregate this information over the entire time interval, this is going to produce the total distance traveled by the car over that period of time. So we don't have to worry about kind of canceling out by traveling forward and then backwards. Here we're going to have the total distance traveled from time A to time B. Now, by comparison, let's think about what happens if we integrate my velocity function, which I'll say is probably what we're more familiar with in terms of the connection between position and velocity. But now let's consider this. The same result happens with the units. Velocity is measured in kilometers per hour. Time is measured in hours. So this is going to give us a constant that's measured in kilometers. Unlike speed, though, velocity measures the rate at which the car is traveling while also accounting for direction. So this means that aggregating the velocity information over a time interval produces the displacement of the car during that period of time. So in this instance, if I travel 2 kilometers to the right, the positive direction on the x-axis, and then 2 kilometers back towards the left, then my total distance is 4 kilometers, but my displacement is 0. So we're going to account for that direction. So when I talk about displacement, we're going to be able to measure how far we are away from where we started. So displacement from time A to time B. So let's think about, I am going to have a separate video focusing on examples, but just to really make sure that the distinction is clear, let's think about a small example here. So we're going to assume that we have a car moving along the x-axis with velocity 1 minus t kilometers per hour. And let's assume that we are interested in looking at the time interval from 0 to 2 hours. So during the first hour, the car is traveling east, if you want to think of that as the positive direction, because v of t is positive between t and t equals 0 and 1. So if I think about graphing the function 1 minus t, this is my v of t, And this crossover happens at t=1. So during the second hour, the car is actually going in the negative direction. So let's say west, because we see that the velocity is negative. So notice that if I wanted to compute the displacement over those 2 hours, I would just integrate exactly this function. And we're going to get 0, which we could see by either computing that integral or noticing that we have equal area here. One is positive and one is negative. However, if I wanted to find the total distance over those 2 hours, we would integrate the absolute value. And we have to be careful when integrating absolute value. We've seen this when we were first looking at the definition of the definite integral. If I'm integrating an absolute value function, then I have to be very aware of where the original function is positive and negative. So having looked at my graph of v of t here, what I can see is from 0 to 1, v of t is positive, so the absolute value function doesn't change that. But when I look at v of t from 1 to 2, which is here, v of t is negative, so the absolute value is going to bring that back up. So this is a graph of the absolute value of v of t. And it doesn't matter necessarily that I can graph it, but I do need to know where v of t is positive and where it's negative in order to evaluate the integral of the absolute value. So now I can see, again, we could use geometry, but I'll just point out that in computing this integral from 0 to 1, I'm going to integrate exactly the function 1 minus t because the absolute value didn't change that. However, from 1 to 2, I'm going to integrate the negative of that, and that's reflecting that I'm flipping that function up. So this would give us the desired integral to look at displacement, and we can go through and evaluate this, and you should note that you get 1. Again, my units in both cases here are kilometers, and so we see that we actually end up back where we started, hence the displacement of 0, but of course we did travel. It just happened to be towards the right and then the left. So in these problems, it's going to be really important, of course, to pay attention to what's being specified. Is it the total distance or is it the displacement? And we have to be very careful when integrating the absolute value of a function, as we've seen in this example here.